Okay, so here we are again. This is another app that there's a link to on our webpage. You really should be playing around with these apps. This shows you position versus time for a ball that is dropped near the surface of the Earth. You could also do velocity versus time. All right, but let's look at position. So again, we've done this problem a lot. It looks like it's going to fall for 2 seconds. All right, so hopefully we know, or you should figure out, if it's released from rest near the surface of the Earth, it's accelerating at about 10 meters per second per second. All right, so then how far will it fall? Well, one way to think about it is since V average is distance over time, that means distance is V average times time. So if it's falling from rest for 2 seconds, it's accelerating at 10 meters per second per second. So the final speed is going to be 20 meters per second. That's the final speed. The initial speed was 0. V average is the average of 0 and 20 in this case. That means V average is 10, and it's falling for 2 seconds. So the displacement is V average times t, 10 meters per second times 2 seconds, 20 meters. Yeah, let's play the thing and see what it looks like. And there you go. All right. Notice something else here. Galileo's law of falling bodies. Notice that during the first second, it's fallen 5 meters. What Galileo discovered was that during consecutive time intervals, the distance it falls during those intervals are odd multiples of the initial distance. The initial distance here during 1 second is 5 meters. The next odd multiple of 5 is 15 meters. That means between 1 and 2 seconds, it falls 15 meters. Additionally, from the 5 where it was at, that means the total distance that it's fallen after 2 seconds, yeah, it's 20 meters. 5 meters plus 15 meters. Now look, and also over here you can see a nice graph of the ball. The time intervals in which those pictures are taken are the same, and the distance increases during equal time intervals. That tells you it's accelerating. It's moving faster and faster and faster. Boom, and the arrow, that represents velocity. That's getting greater as well. So now let's look at velocity versus time. Same situation. Released from rest, it's going to fall for 2 seconds. And bloop. Look at that. Velocity increases at a uniform rate. It's gaining 10 meters per second every second it's falling. So after 1 second, it's going 10 meters per second. Look at the graph here, right? 1 second on the bottom, 10 meters per second on the left. And then after 2 seconds, yeah, it's going 20 meters per second. All right, so let's check out motion number 2. That is a ball dropped from rest on the moon. Crazy. Okay, it's gonna end up having the same speed here. So let's just run the simulation. And bloop. Okay, so this is not actually playing out in real time. That's okay. Notice it's fallen for 10 seconds, right? And it fell 20 meters. Ooh. How does that compare with on Earth? It's falling a lot slower on the moon because the rate at which it accelerates near the surface of the moon kind of depends on the mass of the moon and the radius of the moon. Gravity, the force of gravity on objects near the surface of the moon is less than the force of gravity on objects near the surface of the Earth. Okay? Let's look at position. Okay, notice. Galileo's law of falling bodies works everywhere. It's kind of sort of universal, all right? Check it out. The numbers here are different, but the ratios are not different. They're the same. So you can see here that in, for example, 5 seconds, it's fallen 25 meters. That means that in the next 5-second interval, the distance it falls is the first odd multiple after 1 of 25, which is 3 times 25, which is 75 meters. That's how far it falls between 5 and 10 seconds. So 25 during the first interval, 0 to 5, and then 75 during the next interval from 5 to 10 means it fell a total distance of 100 meters in 10 seconds. All right. Now, one more thing, let's look at velocity again. And we can calculate the acceleration of objects near the surface of the moon by looking at this graph. It's approximate. So then let's run this thing. Point, right? So acceleration, that's the rate of change of velocity. So it goes from 0 to 20 meters per second in 10 seconds. So how much speed is it gaining every second? That would be 2 meters per second. Per second. Yeah, so that's its acceleration on the moon. It's about 2 meters per second per second. That's definitely less than what it is on the Earth, which is about 10 meters per second per second. Let's look at motion number 3. Oh, that's a truck accelerating from rest. Guess what, folks? The graphs are going to be the same as we've been seeing. The numbers are different, but if it's uniform acceleration, the physics is the same. So position versus time. And here we go. Run. Okay, cool. It's a parabola because the distance is 1/2 AT squared. Also notice the distance between these little dots the truck is leaving behind. Each of those dots are at equal time intervals. And then check out Galileo's law of falling bodies. So during the first 5 seconds, it moved 12.5 meters. That means that during the next 5 seconds, from 5 to 10, the distance that it moves will be 3 times 12.5. All right? And then that plus 12.5 add up to 50. Let's look at velocity versus time. We can use this graph to determine the acceleration. And bloop, okay. So, you tell me, what is the acceleration of this car? Acceleration, that's change in velocity over time. Well, it went from 0 to 10 meters per second in 10 seconds. Oh, wait, its acceleration is 1 meter per second per second. That's pretty reasonable, I think, for a car. And then finally, you'll have to remember to tell me this in class. Yes, a ping pong ball accelerates along an evacuated tube. What? You can't be serious. Yes, I'm totally serious. The first person to mention ping pong ball cannon in class on Monday gets a cookie. A cookie. Yes, ping pong ball cannon physics. So here we go. This is going to be slowed down a bit, all right? Boom. It's the same physics. It's the same graph, same picture. The numbers are different, but all the proportions are the same. This thing went from 0 to 20 meters per second in 0.2 seconds, 0.2 of a second. That is not a lot of time, right? 20 meters per second is pretty fast, especially to go from 0 to 20 in 0.2 seconds. So the acceleration is 20 divided by 0.2. I'm thinking that's about 100 meters per second per second. It's craziness. And then if we do the position versus time graph, it's going to be parabolic, of course. And yay for Galileo's law of falling bodies here. Right, during the first tenth of a second, at 0.1, it moved 0.5 meters, half a meter. During the next 0.1 seconds, it's going to be 3 times 0.5 or 1.5 meters. And 1.5 plus 0.5 is 2 meters per second. I'm sorry, 2 meters total. All right, so then there you go. You need to play with this yourselves, all right?